room is on the second floor, so the adjacent building's got 2 floors, on the roof and up down. Typically, you go up into a corridor and put your pipe down a corridor. The existing buildings, usually they've got pipe and cable tray and stuff in there already. It's real hard to get stuff through there. We've actually, in a situation similar to this, that's what we did. We went up over the building, over the roof, and came back down there in the building. So it's really, you don't have a lot of information. If we're giving you a lot more information, you can delve into that. But basically, I think what David and those guys are going to want you to do is run the pipes between them.
Yeah.
And show where, you're going to come up underneath it. And, if you come underneath it, you've got to get into the raised floor and hit T's and take your pipes and go this way and that way. If you come from overhead, you got to get under the floor so you get to the cooling equipment, whether you're going to use air handling units on the floor or whether you're going to use door coolers. So it's
right. So the answer is there's nothing exists. Okay. You have to build it yourself and say how you're going to do it.
Okay. So on the cabinets, there's a specification that says, I think there's 40 cabinets that have to have specific control access. What does that actually mean in this case? Do we need
a
fence?
Fence,
okay.
Gate. And usually the gate's got some kind of access control with a list somewhere that people keep up with, so I can take some training and get in there. It's not a classified thing where you got to have sound barrier and optical barriers.
Right.
It's just something to keep Joe or Bob or Bill from just walking in there and hitting the button. And in one case, I know where we've got this. It's a chain link fence.
So we don't have to have the locked cabinets necessarily, then just the fences only? Okay.
The cabinets, most all the cabinets all come with a lock, but they all got the same key. There's about 1 million of them floating around, so I don't know what it's worth really to do that. But, typically, if you got to control access to something, you control access to your room. You know who's going in and out.
Right.
Okay. Where within the space we have, where is the networking connectivity coming in?
Networking connectivity, if you look on the drawing on the left side, there's, I think it's designated as a telecom room.
Oh.
You got a drawing?
Did you print out the newest ones?
No, these are the old ones.
Okay.
Old ones.
That's fine.
That's the one. That's the first one. That one.
Common. Now that common room is vertical. There's 4 floors and they stack one on top of the other, so all your comm cables go straight up. Usually your trunk lines land in the first floor.
So everyone can see.
It's on the
that
bit.
side.
Yeah, it's on that. That's right.
That's on this one. It's drawing 3.
Right. It's the
okay.
drawing of the data center room itself, by itself.
Yes.
Typically, you want to stack your comm rooms. You've got a multi-floor building. And that's the case here. And bulk cables, bulk fiber, bulk twisted pair, or flow lines. We don't do twisted pair or anything for phone lines. The bulk fiber comes into the first floor and then it gets patch panels and it goes to the second floor, third floor, and fourth floor. And you might have 2 different kinds depending on if you've got classified stuff or anything like that. And then once you get into the second floor, you get a patch panel, and then you have racks with switches and whatever else you need in there. And each one of these rooms will have, in our case, will have a generator backup power to it. So we have to supply UPS, which is in this room, by the way. You don't have, well, assume it's not in there. And you can get rack-mounted UPSs, you can get floor-mounted UPSs. You can get them that are monitored, and that's really the way to go, is get something that's monitored. You don't need a lot of power in the telecom room like you used to, because all this stuff is fiber optic.
Right.
And the switches are real low power. Just switches and fiber optics. So HVAC equipment in the telecom room is nothing. What if the power, let's see, the power goes off, the generator's running all your switches and everything, you're producing heat, but your fan's gone off, or your chiller's off. What do you do? Now this, in these cases, what we opted to do from the get-go was to put a little pump motor on the chill water line. So when the power pump went off, this pump would stay on and keep pumping water. Because you got a water pipe this big around. And it's got thousands and thousands of gallons of chill water. And we keep the fan running on the generator also. So we actually can cool those rooms during that time without any HVAC equipment. But it's not a lot. And we've had outages where we went 8 hours with power in these rooms and they stayed cool. So that's something you have to consider, because you get backup for your computers. You gotta then turn around and get backup for everything that supports those computers, because if you don't, power goes off, the lights stay on, and then it gets 400 degrees in there. You have to shut everything down. So, anything else?
So I have.
Sure.
For after telecommunication room, do we get single mode fibers?
Single mode?
So like we have telecommunication room that get all of its transmission, like fiber communication.
Yeah.
So those fibers can be single mode fibers or multiple mode?
Multi-mode? Usually over short distance, you do multi-mode.
Yeah,
It's building to building, it's single mode, because they have much lower losses. But you probably assume multi-mode.
So those fibers connect to another router?
They connect into another router. There's usually some big routers downstairs, and at main, we call it remote data distribution facility, where they actually tap into the big gigabit.
Right.
That's
That's what
like,
you
that's
just-
where all your big machines are with all the, you
So
know,
this
you
is-
usually go multi-mode down to
This is one data center within a multitude of data centers maybe in the building.
Okay, so then we're gonna get another cascade.
Correct. Okay.
There was a statement on here where it says 40 cabinets are required to dual feeds, tier 3, and then it says 20 to 40 cabinets have the specific access control, which we talked about earlier.
Right.
But it says specific access control areas were required to accommodate an additional 20. So are we looking?
You need room to add another 20.
Okay.
So there's expansion capability within that area.
Have a total of
40. Right.
Okay.
And
And
not
are
just-
all those 40 dual feed, though?
That's a good question. I would say yes.
Okay, let me make a point here. We deal with computer science guys. How many of you guys are computer science guys? Don't be ashamed. When we deal with computer science folks, they don't always tell us what we need to know. We have to go back and ask questions like you're asking right now, because they have a picture of what they're wanting to buy and what they want us to put in. We know what we have to do to connect up to it to make it work like they think they want it to work. So it's a good question, and when you was reading it, I thought about it. Oops, we forgot to put that in there, but it's good that we didn't put it in there because we can answer it now.
Right.
You have to go back and you have to talk to people. When you're a facilities designer, you have to ask people questions and get stuff out of them, because they're not used to giving information out like you need it. They're used to working on the research or the programs or something like that. And we have specific requirements for electricity, chill water, or safety, and all those other things that we have to address. So we have to educate the computer science guys just a little bit when we're doing this stuff. But that's our job to do that. It's not their job. If we mess up and don't do something, it's not their fault. It's our fault because we didn't ask them. We're supposed to know to ask people like that. And if you have an AE firm and you're building a computer center or something, and they don't ask a lot of questions, you better get ready for a lot of things to go wrong when they turn stuff on and say, why do you do this? Why do you do that? You want people asking lots of questions, and that's the first point I want to make before we get started.
So did you get it?
Well, we
Answer?
weren't sure if it's supposed to be a total of 60 dual feed, so 40 with a capacity for another 20,
Right.
or
That's,
if it's just 40 with 20 growth being that 40.
I would say since and Rick can correct me if I'm wrong, since they're asking for dual feed for the first 40, I would assume you'd have to scale to the additional 20 to
That was the
dual
intention.
feed as well.
I'm a computer science guy. That was my intent.
Right.
I didn't write it. That's what I.
Right. So yeah. So the capacity is 60.
60 dual feed.
Dual
40
feed.
You gotta have floor space for 60. You gotta have infrastructure for 60.
Right.
You're gonna put in 40.
40 to secure at max.
And if it's secure, and that 40 is gonna be out of the total. What do we have? 120. 40.
Right.
40. Yeah. That's gonna be out of that total of 140.
Okay.
I think the other 140 didn't specify dual core design, or didn't specify.
Well, there's just 140 altogether.
Yeah.
So wait, it's 140 plus the 20 possible.
Correct.
Yeah,
Correct.
So-
but you're designing, you're gonna buy equipment and put in stuff for 140. Unless you have to go up to the next level and you have that space in there. You know, you can't buy exactly what you want. You know, you have to buy things in steps. It's like, and you have to always get the step higher. So you may end up buying more than what you need enough to cover the 20, so when they come in with it, it's just
there.
put it in.
Right.
Or you may just be right there at the top and then go back to another, you know.
You have to plan for the 20 somehow.
Yeah.
Well, we were thinking in terms of spacing,
Yeah.
Right.
so we need to make
You
sure we
need to
have
ma-
space for
That's
20.
right.
Yeah.
Question in the back.
I think I read it.
Okay, you good? All right. Okay, Rick. Well, Rick's going to cover the electrical. I believe it's the right way to say it. And so he does this in his sleep. And sometimes I'm not sure. Yeah, that's right. So again, you may have some questions at the end, but Rick, why don't you go on and kick us off here?
I'm Rick Griffin. Been doing this 38 years, okay? Not computers, but I've been in electrical engineering 38 years. I've run utilities, I've done research, I've been doing high performance computing facilities since 2001. And back in 2001 when we started, we looked around for AE firms, architectural engineering firms, that had experience in this, and we couldn't find it. 10 years later, they come to meetings and they say, we got 30 years experience. And I look at them and say, where were you guys 10 years ago? But a lot of stuff we've learned is just doing it. And we've had the good fortune of having 2 very large computer centers, and we do something here and it didn't work, we'd fix it. Next time we'd fix it up here. We'd do something up here. So we've had this really intense iteration going on with our applications and with our infrastructure. But before I get into the electrical stuff, I want to throw something out here. Now, when we have intern students come to the Oak Ridge and work for us, like I said, I've been doing this 38 years, and I've learned a lot of stuff about people and about things. When I was in school, I'd go to class like this. Professors start drawing stuff up there, like these equations for the op-amp. I remember that class very well, and I remember sitting there, and as soon as he started, I started daydreaming and inventing all these things I wanted to do. Well, I didn't pay any attention to what he was saying. Went home I would go home at night, stay up till 2 o'clock in the morning, study, and come back next day, do the same thing over and over again. I was behind the 8 ball. Went to school with these 2 old boys, and they were just plain old guys, and they studied quite a bit, but they asked lots of questions, and they made straight A's. And they weren't that smart. I mean, you would think these guys, I mean, literally they weren't, but they made straight A's. Didn't realize what was going on until I did my first job. They sent me off to school to take a class. It was speed learning and not speed reading. And the whole gist of the course was that when you go, for instance, when you read a newspaper article and you get halfway through it and it mentions somebody's name and you don't know where that character is, you got to go back and reread to find out who that guy is. You ever had that happen to you? You go into meetings, you don't have a clue what's going on. The point I'm trying to make is, and they made, is that before you do anything, an activity, whether it's a class, reading a book, doing a project, going to a meeting, anything, make sure you got questions in your head about what you're getting into, what's there, who, what, when, where, why, and how. Those 6 questions. You know, who's doing this, and what do you know about that fellow? And if it's a really important meeting, you need to know as much information as you can about that meeting before you go into it. Or if it's a project, do your homework. Find things that the questions you got. Now, when I answer your questions, it sticks, right? And questions are kind of like Velcro. When an answer comes along, it sticks to it. If you don't have the question in mind, the answer comes along, it bounces off and says, wait a minute, what do you say? You know? So, in this class, please ask questions. And I'm going to try to attempt to use this approach and feeding you guys information. I'm going to ask y'all to do things that you don't have any clue. You're going to say, what's he talking about? Okay. Then later on, we'll fill in that question and we'll answer that question for you. And hopefully, it'll be easy to remember. There's 4 classes that I'll be teaching. You can see there, first one's on safety fundamentals, electrical jargon, calculations. And we'll get into talking about the project. And I've got a couple of homework problems, and I've got one just for fun that ought to be interesting to you. And then next Tuesday, we'll talk about electrical equipment and talk about all the ins and outs of the equipment for you computer science guys. This may be, that may be what you're hearing when I'm up here talking, but it's really fascinating. I mean, there's a tremendous amount of stuff that goes into making a computer system work that has to feed it. And you'll see some of that in just a minute. Telecommunication codes and standards, my favorite. Then we talk about metering and SCADA, load factors, capacity, and efficiency and sustainability. And I'll spend a lot of time on this and on reliability and power quality because it's kind of one of those little nuances that it's kind of like a caviar, I guess, for an engineer. It's one of those things that's really getting into the minutia that really makes a lot of difference if you know what you're doing. And I'll try to share with you a lot of our experiences and things and what we've learned in the years from that. 22 minutes. I'm not doing too well, am I?
Well, you started off with questions, so
Okay, here we go.
you'll be fine.
All right. We have a secretary. She's really good at putting all this stuff together. Me, I'm a white sheet of paper and text guy. That's all I want to do, because everything else for me is a distraction. She got hold of what I did and put all this stuff in there. I have no idea what that stuff is, but it looks really good, right?
I'm gonna tell Jennifer what you're saying.
I told her that. You know, she knows that. Okay, as far as safety goes, if you have an opportunity to work around electricity and you see electricians and they got a switchboard open and they're looking around, do not go in there and look in that stuff. The way OSHA's written, the way all the programs for lockout, tagout are, you got to be trained. You got to have a lock on a box that has a key in it that goes to the lock that holds that breaker open to keep somebody from cutting it on. If you get in there and somebody cuts it on, you know, you could get electrocuted. We'll show, this fellow here is a champion. I love that video. And there's training for electricians. Now, ORNL just went through a big training. We trained thousands of people in electrical operations. Not just electricians, but researchers and people that get around this stuff. I had to take all of it all the way up to the medium voltage stuff. If you're in a data center, and in the government, we had at SLAC laboratory, I forget which laboratory it was, some guys, you'll see this right here, this happened to those guys, and as a result, the lab manager got fired, and this DOE just came down on all the labs and said, no more hot work, okay? And by hot work, I mean, you pull the cover off a live panel, you take a screwdriver in there, and you start touching energized stuff, turning screws and taking breakers out, and people used to do that all the time. And they were doing it. So when that came down, we thought this is going to kill us because we can't get in there and make changes. But what it's forced us to do is to think ahead. When we have gear down, we put spares out to boxes. We do things to think ahead so that when something happens, we just go out there and open or take a lock off breaker or well, connect to the wires, take the lock off breaker and close it. We don't have to have outages, but you can live without that. Accidents don't only hurt people, but they affect your bottom line, because when you have an accident, you have to shut down things, you got to investigate, you got to find out why it happened, who all was involved. Then there'll probably be lawsuits, and then it's just a big mess. In addition to that, you hurt people. I had a video of two guys trying to steal copper wire in a medium voltage system, and they were literally burned like barbecue. I mean, it was awful. I didn't show it because I figured we might have a weak stomach or two in here, and I didn't want to upset anybody. This one here is pretty bad, so I'm going to let you see these videos real quick. I'm not going to. Let's see here. I'm going to try to jump ahead to where the good stuff is, but get them to load up. Okay, come on. You may not watch all of them. It's taking a lot of time. You got to be careful when you do this, because you don't know what's going to pop up over here on this side. You know, so, I've had that happen. And I had this next. All right, here we go. This is medium voltage switchgear. It has breakers, and the breakers plug in. And you take them out, take them over here and work on them, plug them back in. And you got this little thing you turn to make them go into the stall and turn to come out. They now make electric motors you can put on them and do it remotely. So let's get this old boy here. See you guys working on it there. About right here. All right. Watch this guy. This guy's got a cotton shirt on. And
Oof.
Look.
Oh, wow.
Look how long it lasts. Now the reason that happened is because some overcurrent device upstream didn't work, and it just kept arcing and arcing. I've had that when I was in the utility business. I almost got a bunch of guys killed because I let some people work on a line hot. They got the lines together. The substation battery was dead. The breakers didn't trip. And I've been home on the other end of town shaving Sunday morning, and my lights go, and stay down for 30 seconds and come back up, and do it twice. It was a relay at TVA substation that tripped, saved these guys' lives. So I've seen that happen.
So the emergency lights didn't come on.
Well,
Do they have any?
they may have, but the room was full of smoke.
Oh.
See, not only you get the arc flash and it literally melts your skin. Now,
It's gonna play.
It's
that.
going to play the
Yep, let's
next
go to the
one. You
next
don't want to do that. Yeah, you want to go back.
now this one here is the one I love. This little boy here's my hero.
So what happened to the fellow that was?
Well, they're
in
severely
there?
burned. I mean, they have to have face reconstruction, and a lot of times it gets in their lungs. It usually ruptures your eardrums because it's a literal explosion. Now this is, I think it's a UT student. I don't know. I'm just kidding. Just kidding. I'll tell you a funny joke here in a minute. But that is an energized contactor. And apparently he's an electrician because there's some electrical
Oh
stuff.
gosh.
Now, it's probably 120. Now this is what happens to you when you get shocked. He's going to demonstrate that. Watch it.
Oh,
Yeah.
God.
You see how his muscles just involuntarily flexed on that? And his arms went up?
Well, luckily he could,
Okay. Now that's what'll happen to you. Now, the interesting thing is, well, I'll talk about this in the next slide. This
So
one right here.
nobody in this room would do that, right? Yeah, well, there's
Hey,
I don't know.
I'm shocked. I've been shocked. I mean,
Yeah,
I hate to
I'm
say
back
it, but
into
I've
it.
done stuff like that. So this one right here. Now this is electricity kills you like that. Okay. Now these guys are Chinese workers in a factory. They're pushing a bamboo scaffold around in a wet floor, and there's apparently a 2400 volt or a 4160 volt right overhead.
That looks like a party, didn't it?
Yeah, I gotta
That's
skip.
the ad.
So my 5-year-old grandson says when I'm watching train wreck videos, he said, "Okay, skip the ad, Paul." There we go. And they're walking around, they're thinking about what they're going to eat for lunch, they're thinking about their families, they're thinking about their oppressive government. There's no telling what they're thinking about, right? They're alive 1 second. And I'm going to stop it because it gets really gruesome. They start burning. I mean, this is an awful video. Look at it. What do you think they're thinking about? Do you think they're thinking about dying? All right, keep going, guys. Come on.
What is it that they're doing?
It's a bamboo scaffold.
That's the way they
with
do
wheels on it.
scaffolding. They don't buy,
Watch this. They're dead. See how it killed them? Now,
because
wait a
they
minute.
ran into the electric,
Yeah.
to the left.
That
of
thing
it.
became energized. They're on a wet floor.
Wait,
Look at
what
them.
came?
They
Drop it
hit
off.
They hit the thing on the
Now this guy's starting to burn over here.
for them
See?
so they can see it because it did happen pretty quick.
So enough of
I
that.
don't see what they hit.
It's up to the
It's
left
up
at the
high.
top.
You can't see it.
It's a white-
It's apparently a line up top.
At the top,
The
This-
bamboo?
and the bamboo conducted.
Yeah.
Oh.
Yeah, they got into something
And then
because it killed them.
they were in the wet. The floor was wet, and so they couldn't get away from it. It didn't knock them back, so they caught them.
I've talked to a fellow who told me a story about a lineman. He climbed a pole, opened a recloser up, several poles up, climbed the pole, was working on the line. And he said the next thing he knew, he woke up and his back of his head was hitting his heels. He was on a belt on a pole. And what had happened, his buddy came in behind him, closed the recloser, and energized the circuit. And he said what he remembers was that his whole body vibrated at 60 hertz. So that was it. So there wasn't a thought or nothing. It was just, and then it went dark. And then next thing he knew, he woke up. He lived to tell it. It blew a hole in his arm, went in his elbow. When his arm went out his elbow, he lived to tell it. But that's maybe what those guys felt right before they went into wherever they're going. So, the point I'm making is electricity kills you like that. And that switchboard right there, they all look just like that right before they explode. Not a bit dangerous. You got a steam engine that's over pressure, you got valves popping off and all kinds of things happen. You kind of know something's going to happen, but you don't with electricity, so you got to respect it and keep your distance from it. Here's a little tidbit of information. AC is a little more dangerous than DC. Back in the early part of the century, Edison and Tesla were in competition to electrify America, right? Tesla had AC. Brilliant man. Come up with all the three-phase stuff right out of his head. Edison over there competing with his DC. The problem with DC, it wouldn't go very far. You couldn't transform it up to a higher voltage at a lower current, transmit it and bring it back down. And he had to put generators everywhere. Tesla came up with the transformers and all that other stuff. So long story short, Westinghouse and Tesla got together and they energized America with AC. That's why we got AC right now. Westinghouse eventually got all Tesla's patents and Tesla died pretty much poor. Westinghouse, you know that story. Nowadays DC's coming back, but it's only on the high voltage and in the distribution in buildings because of solar panels, fuel cells, wind generators, things like that, because they're creating DC and converting it to AC is a loss, so you want to use the DC. But anyway, how many of you got GFCIs in your restrooms, bathrooms? All right. Do you know what those what current those things will trip off at? Let's say you're in a bathtub and somebody throws a radio in there and says, hey, watch this. The GFCI will trip, but you know what amperage that it trips at? 6 milliamps. And it trips just like it's almost instantaneous. So you feel, boop, that's all you feel, right? And that's why you have them in the bathroom. So if you get water if you get in water with electricity on it, it'll trip the thing off immediately. So 1 milliamps barely noticeable. 6 milliamps will make you twitch. 16 milliamps, you can't let go, just like the guy in the video. 20 milliamps, you can't breathe. And then 100 milliamps, you get ventricular fibrillation where your heart just sits there and goes, it don't beat, it don't do anything, it just sits there and quivers. And that's where you have to defibrillate people. On DC, the currents are higher. And by the way, these numbers here are lower for ladies because of the lower mass and things like that, but still bad. So remember those numbers. All right. Now, how severe your shock or electrocution is dependent on how long it lasts, your body resistance. I've known electricians with real callous hands that would actually touch 480 volt stuff, wires. Didn't shock them. They had these dry calluses on their hand. They were good insulators, right? And let's say you're standing on a floor and you got some really good insulated boots and it's a dry floor. Conceivably, you could touch 120 volts and it wouldn't hurt you. You might feel a little tingle because of the capacitance through your body to ground, right? But if you're insulated well enough and have a low enough capacitance, you could actually touch it. Now, if you take if you're cut, you got an opening in your skin and you're bleeding, and you do that, it's serious business because then you don't have that skin resisting the current flow. So be careful in sweat, things like that. So you shouldn't have any occasion in a data center doing this stuff. You're going to have electricians doing all this stuff, but folks do plug and unplug power supplies and racks and things like that, and you have to be aware of this stuff. Now, if the current's 500 milliamps for 0.2 of a second or less, or 50 milliamps for 2 seconds, you're probably going to make it, okay? But longer than that or more than that, you're probably going to have a problem. Now, if you get current through your chest, in the right arm, out the left arm, goes through your heart, that's got a better chance of causing the fibrillation. So you want to keep one hand in your pocket, right? The old boy is sitting in the floor. Now, if he got it on this side and this side, I just wondered, did he kill him? And low frequency AC is more dangerous than high frequency AC. I actually saw a guy one time, he had something called an inductive therm. It was a metal furnace, had 1,000 pounds of iron in it, had a copper pipe around it, and it was pressurized at 60 psi, which is very unusual for furnaces. Usually they're vacuums. And it's unusual because if the thing explodes, you got all this molten metal going everywhere, okay? You circulate water in this copper coil and you put 1,000 volts, 1,000 hertz, and 1,000 amps through that coil. And it inductively heats the iron, right? Had 2 power supplies, and they were sitting right next to each other like this. And the big switch to disconnect this one he was working on was open, but the terminal lugs where the copper pipe connected to were touching each other. And the only thing that was keeping direct contact between those two things was some paint on those terminals. The guy reaches up there and grabs that stuff, and the guy said he just went, stood there for minutes, they thought. And finally his arms got tired and he collapsed. Took him to the hospital, he's all right. But it was 1,000 hertz. It was, if it had been 60 hertz, it would have killed him. So the higher frequency stuff is not as bad. You've seen these guys with Van de Graaff generators or Tesla coils, and they're drawing these big arcs or whatever. That's real high frequency stuff. The Tesla coil is real high frequency. The Van de Graaff's DC. But usually that's infinitesimally small currents with high voltage. And about all it does is punch a little pinhole in your skin. Now, electrical equipment, maybe you'll get into this, but you go buy a piece of gear and it's got some 50 volt, or say it's got some 24 volt control stuff. You can touch the 24 volt stuff. but they'll stick it right in the middle of a 480 volt cabinet. We want to ask them to separate the stuff, and we get manufacturers to do that for us, to segregate the low voltage stuff over here. We can work on it where the controls and PC boards and all of this stuff are. But look for that kind of stuff, because people are starting to do it. Manufacturers are doing it more and more now, but used to, they just mixed it up because everybody worked everything hot. Nobody cared. Okay, I'm going to get into electrical generation, and we're going to talk about power. Okay, I'm going to start at the generation end of it. Got these numbers off. The next slide is really a fabulous slide. I love it. Best slide I've ever seen. But this tells you about what the percent capacity, about 40% coal, 27% natural gas, nuclear, and hydropower. This is the bulk of the power that's being generated. I'm not sure that number is that high, but it's still, you can see what's happening with renewables here. There's a long way to go before they'll ever replace what we got here. And we're going to be using this for a long time. Now, the interesting thing is the efficiencies of these things. You take a ton of coal, or you take a equivalent kW of coal, you're going to get 480 watts out of that. And 32 to 48, depending on how old the steam plant is and how efficient. With coal, you create steam. You only get so hot with the steam, then you run it through a turbine. And how many of you had thermodynamics in here? Okay. How do you make something more efficient?
It's been a while.
Okay. You increase the delta T. In other words, the hotter you can make your turbine steam and the cooler you can recover and feed back in there, the more efficient it will be, right? So they can only get so hot with the steam. With the natural gas, they feed it into a gas turbine. And then the exhaust comes off the gas turbine, goes to a steam generator, feed it back through a turbine, and they get to double. See, they basically are using a much higher temperature range, so they get 60% on some of these things. Nuclear is about like coal, because nuclear just boils water, and it can only get so hot. You don't want to get it real hot because your reactor will go floating through the floor. Hydropower, this is losses in the generator and piping and stuff like that. Biomass, it's going to be like this because biomass creates a gas. It takes organics, heats them up, drives off the volatiles, and the volatiles are what power the furnace. We had one out at the lab, and it was on wood chips, and you heat the wood chips up, and the volatiles come off, they burn the volatiles, and you're left with carbon. I don't know what they did with that carbon. I think they made pencils out of it. But, and by the way, that turned out bad because the wall of the burner got corroded and it compromised the boiler, so they had to shut it down, brand new boiler. And of course, petroleum can do the same thing natural gas can, because you can run it through a turbine. Then you got wind generators, you got gears, you got all kinds of electronics in those things, not without problems. And then gases, this would be syngas or something like that, would be on the level with natural gas. And geothermal. Geothermal is about like nuclear. You only get so hot with geothermal. You know, you pump it in the ground, get it hot, create steam. You can only get it up to a certain temperature. And solar is 12%, and that's a good number. I read something today where, I don't know who it was, one of the labs has come up with a silica-based film they could put over a solar cell that will reflect the infrared but let the visible light go through. And it actually cools them down like 23 degrees Fahrenheit. And the cooler a solar cell is, the more efficient they are. So they've actually been able to gain 1% efficiency, which is an incredible thing. Of course, the film would go on cars or anything else you want to stay cool in the summer.
What about methane? Is
Methane,
part of
like
natural gas?
that'd be biogas, like a landfill. Yeah, same thing. It burns like natural gas, syngas, all. Now this is a load curve. It's about 40. This is 40 kW here. And if you've been to Oak Ridge, there's a big array of solar cells on Bethel Valley Road. You guys know where they're at. And that's the load curve for them. This is over several days, the month of September. Each one of these spikes is a day. So you can see at night there's nothing going on. Had some clouds this day. Now, if you're going to run the world off solar power, what do you got to be able to do? Pardon? Store it, yeah. And how are you going to store that much power? And one of the things I got at the end of the course today is to basically do something like that. It's fun. It's real simple. This is a fun exercise I got for you. But But this is basically a sine wave. If you got fixed solar arrays, it'll be a sine wave. If it's tracking, it'll be more of a bump, square wave. This is the chart I love. This was done by, I got to give you credit down there, LNL, Lawrence Livermore, and DOE made this chart. So there you go. There's the commercial part. But it is a marvelous chart. Take it home when you get home. Download it off the site and look at it. This is solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. These aren't the scales of how much is produced. These are, okay? This is the energy that goes into generation. And about 30% of it just goes out to cooling towers, right? Here's the other, 70% of it goes out to cooling towers. 30% goes to residential, commercial, industrial, and just a little bit to cars, okay? Here's where oil goes. We get a little bit to generation, not much. Some to industrial because you have petrochemicals and whatnot. Majority of it goes to transportation, okay? Let's say we went to electric cars, every one of them. You'd eliminate this thing right here, and you'd have to put it up here on natural gas or nuclear or even coal, maybe wind. But you can see what a stretch that would be to take this and to put it on wind or solar. You really got to build a lot of stuff. And it's not a near-term solution, maybe in a long term. But this is a wonderful thing. I think this was great, whoever did it. And it's pretty recent, it's 2013. Here we go. Now talking about generators, they typically generate power at about 13,000 volts because the wires are real small and they have to do the windings. That voltage goes into a switch yard, a TVA substation or whatever, gets jumped up to higher voltage and transmitted. They're synchronous, and by synchronous I mean that to get a generator online you got to spin it up to speed, and then you get it synchronized with a utility and you close it, and it stays at that speed. And when you put more load on it, there's something called a torque curve, but the generator is still spinning at the same speed. That opposed to a motor, which induction motor, which actually don't go that fast. That's why if TVA was to have an event and shut down all their generators, let's say the sun was going to put out a big corona discharge. We knew it was coming, and it's massive. And TVA, if they don't do something, it will destroy transformers and all kinds of things because of the DC currents that flows to the earth causes this corona discharge. So TVA manager says, shut the whole place down. So he hits the button, all the generators go off. It takes weeks to get these things back up and get them synchronized. You just don't turn them back on and come on like a little diesel generator does. They're usually parallel with other generators. Big, 1.57 gigavolt amps. Volt amps is the way you size electrical gear, not watts. You size chill water plants, mechanical stuff based on watts because that's dealing with real work. Volt amps is watts plus some other stuff that goes on in the electrical system that doesn't do work. But that's a pretty big, that's 1,570 kW or kVA generator, and they're as big as this room. They're huge. I mean, they're very, very huge. At 1,800 RPMs, and if you want to click on this, this is Hitachi. They've got some of them. You can see pictures of them. Natural gas turbine. You've heard of distributed generation, CHP. If you do it in a big way, you'll buy a turbine, and they can get up, as I mentioned earlier, they can get up to 80% efficient or better because they got like a 60% electrical conversion, and then you take the waste heat off the steam and you heat buildings or do something with it, and you get it up to 80 or 90%. European countries are real big on that. They have steam plants that generate electricity. They take the steam and distribute it through the neighborhoods, so they get a lot of use out of their coal. In America, you know, we get whatever we get out of the generation conversion, and it's a big waste. Hopefully, as time goes by, those kind of things will change, but it's hard to find a use for that waste heat. Combined heat and power plants, as I mentioned, can be greater than 80% efficient. Any questions you may have got? If y'all have any questions, stop, because that's one of the things I want you to do. Okay. To get from the generator to your load takes about 6% of the energy in the transmission distribution system. Not much. You step the voltage up so you can lower the current. Higher voltage, lower current, because the product of these two stays constant. So You raise one, you lower the other. So they'll raise the voltage, drop the current down, run it on small wires, and then drop the voltage back down so you can manage it. You don't want to be hooking up to 13,000 volt stuff. You want to hook up to 208 or 480 volt. And there's different levels. There's medium voltage, 2.4 kV to 69. High voltage is 115 to 230. Most of the TVA lines you see on the big towers are 161,000 volt lines, okay? Some of them are 69, some of them are 46. Those will be on the big tall poles all by themselves. And if you go, you see the big towers, the big wide ones with the three wires on them. Those are about 500 kV. And the reason they use 3 wires is to prevent the corona discharge from getting real bad. If they had 1 wire there, it would really go bad. You can actually stand under those with a fluorescent light and hold it up and the light comes on. The electric field from that wire to the ground is so great. And I've seen them run those things over playgrounds, 2 playgrounds. And one of them, we played soccer early in the morning and it was dew. It's just, that's all you heard. What's wrong with people? But anyway, they also have high.
Now you have one of those at Oak Ridge, right?
We got 2 substations, 161 substations. One of them has 3 lines coming into it. The other one has 4. And you need those because, have you ever turned the water on your house and your water pressure drop? You ever done that? You ever had that happen to you somewhere? That's because the water flowing through the pipe drops pressure, right? Because of the resistance of the pipe. And you got a pressure here, constant pressure here, so your pressure on the end is going to go down. Same effect happens with electricity. And if you just have one of these lines, if you put a load on it, your voltage drops. If you have 4 or 5 of them coming in, it's real stiff. It's a term we use to describe. It's like having you got the ocean on top of the mountain just ready to pump water down to you. So we have like, we got 7 lines. Let's see, no, 1, 2, 3, 4, 5, 6. We got 6 lines coming into our site. And we had 3 at one time. TVA would have a fault on a 161 line 10, 20 miles away, 30 miles away. And that line would arc for about 5 cycles out of a 60 cycle second. And during that time, the voltage would drop because there's so much current flowed into that fault. And then the relays would drop out that section of line and the voltage would come back up. And we were having voltage drops, and I'll talk about this later on in one of the other things we talk about, power quality. We were having voltage drops that were so extreme our computers were cutting off. And we got them put in a 3rd line. Still have the voltage drops, but they're not as extreme, and our computers can ride through them. And that's a very interesting thing we'll talk about later on. Okay, these lines here are where you get most of your exposure because they're out in the open, there's trees, there's lightning, there's squirrels. In 2011, we started having problems with our medium voltage system at ORNL that supplied a big computer system. We had like 17 events that affected computers over the next 2.5 years. 2 raccoons did the same thing, a squirrel, lightning, wind blew a massive tree, just tore down the power lines. A woman drove a car up a guy wire, and when she did that, the lines slapped together and tripped off. And then she drove it off the guy wire, went across the road, and drove it in the lake. She passed out or something. That's it. And let's see, we had a breaker just tripped out of nowhere. We never could figure out what happened. We had lightning strikes. We had all kinds of, it's just like, when's this going to stop, right? Well, we've since taken all that stuff out and we put it underground, new 161 substation. We don't have that problem anymore. But that's where most of your problems will come from, right there. Now, the low voltage part, low voltage being 600 volts and down, right? That's where you're going to do most of your, that's where you do your distribution in your data center. That's what area we're primarily concerned with. To show you that other stuff, to show you there's a lot of stuff out there that has to get power to you. And it consists of power you deliver from your building distribution transformer into your building. There's always something there that the 12470 kV, the 138 kV, or 4160 kV hits the transformer, drops it down to a lower voltage that then can be distributed into your building. In that part of it, you lose another 3 to 6%. 3 to 6 on the high voltage and medium voltage, 3 to 6 on the low voltage. Now this is just straight wires feeding straight into the equipment. You have uninterruptible power supplies, and actually they're not uninterruptible, they're mostly uninterruptible because they never are perfect. And you got a 2-end system which is completely redundant, so you got 2 UPS is running, feeding it this way, and you're running them at half load, right? Because you know when you run electronic stuff less loaded, it's less efficient, right? Because you still got all those losses in there, you just don't have as much power going through. So for a system like that, you have 17–20% losses in it. So when you start talking about energy efficiency, okay, you got a lot of reliability, but your efficiency goes down. So this counter over here says, hey, we need to save some energy. We need to save some money. You do this. This guy says, wait a minute, my computer's tearing up, you know. So it's a balancing act to try to figure out something between the two. Now, the chapter 11, I think that was one you were supposed to read today, had a discussion about this, and it was pretty good. But your configuration depends on what your customer needs. If you're in a laboratory and they're doing research on these computers, every 30 minutes they do something called a set point. They take a snapshot, and if power goes off, they go back to that set point and rebuild it and start over again. If the power goes completely off on a big machine, it's not really as easy as turning the thing back on, because you got all these thermal gradients and stuff cools down, and then when you turn it back on, it heats up and stuff breaks. So they end up usually changing a lot of boards and stuff before it really gets back up to speed. If you work for somebody like Amazon.com, you might have a combination of these things. You might have a one-end system that's just straight off the utility. For us, when we're out here surfing, just playing around, they'll put you on that one. If they lose that, they don't lose anything, right? But let's say you go and you put something in the, what do they call it, little thing? What? The cart. Yeah, you put something in the cart, they said, aha, we might have something to buy. They'll move you up to another system that's got more reliability. And then when you're about to hit the button to say buy, guess what they do? They put you on their most reliable system because they don't want to lose that sale. And people are beginning to do this more and more, because providing a two-end system like this is incredibly expensive. It takes an incredible amount of real estate, and it's incredibly complicated, and you got to have lots of people to work on it, and they got to be highly trained, because the first Bubba or Bob or Bill comes along and says, hey, what's this button do? And I can tell you story after story where that's happened. The stuff gets shut down. Where am I at here? Okay, I've got till
2:25. I mean, I'm sorry, 3:25.
Okay, I've got about 31 minutes in. Good. All right, here's a very, very simple system. Here's your medium voltage. Usually you have a tiebreaker between two buses where you got feeders coming in from different directions, hopefully from different generating plants. You feed a transformer that goes from medium voltage to low voltage. And here I've got a 3/4 MVA transformer, and you'll need about a 5,000 amp switchboard. That's about as big as you can get. You can get 6,000 amp switchboards, but you got to buy them from one manufacturer. 5,000 amps are pretty much so that's about the biggest thing you can bring power into the building. So if you need more than that, if you got like a 15 megawatt load, you'll need 3 of these, right? So you come down here, you hit a PDU, which steps the voltage from 480 down to 208, then you hit your IT equipment. You might have a 480 volt, and this is what we have for the Titan supercomputer. It's this, you don't have this, and you go straight to the computer. That's all we got.
At 480 volts.
At 480 volts. We don't have this in here because we don't have to step it down from 480 to 208. That's all we got. You think, well, that can't be reliable. But there's no moving parts. It's simple. If we do our job checking this stuff here and do something we call predictive maintenance, I think it ought to be called preemptive maintenance, because we watch this stuff. We watch it. As soon as we see something happening, we go in there and react and do something to it. It's pretty reliable. These machines down here can take what TVA's power quality says. So for the bang for the buck, it's pretty good. Plus we don't have real estate. You'll see as I go through these. Now, if you want to do concurrent maintenance, in other words, you don't have to cut this off to work on this, you can do this. Put another line over here. You're going to have to do the same thing with your chillers, right? Most of the time chillers are N+1, but your electrical system's got to be able to switch over for all of them. Chillers have to be taken down and worked on all the time. So that's with no UPS, and this I added this down here. This is a dual corded system. It has 2 inputs. They convert it to DC. So if I lose one input, all the load shifts over here to this input and vice versa. And they usually run about 50-50, right? You can also buy something called a static transfer switch that will draw the load off one side, and if it goes away within a quarter of a cycle, 4 milliseconds, switches over to the other side for you. And you can buy these in little rack mounted jobs. You can buy big 600 amp 480 volt jobs that are just full of electronics. And if you got a single corded load and you want all this reliability, you have to do something like that. And I know places where they've done that a lot. Now here, I put a UPS on this side. Here's UPS. This is static bypass because you have to have this so you can cut this off and work on it. And actually, in all reality, this will be inside this box, so you'll have a physical breaker bypasser in it called a maintenance bypass, okay? So now, I added a cold water storage tank here. And the reason I did that is because I could ride through power quality events where the voltage goes down, comes back up, and keep my loads going. This side over here will see the dip, but it won't affect it because I've got the UPS riding through it. But chiller plants, pumps, chillers, they have, if it got VFDs in front of them, variable frequency drives.
How about the surge protection?
Pardon?
How about the surge protection?
Surge protection?
Oh, we'll get into that. You used to hear computer folks say if something happened, it was a surge. Well, now we've got all kinds of instrumentation, and nobody says that anymore because it's not a surge. It's not, and if it's power quality, we know it. Usually it's go back to your computer and figure out what's wrong with it. Quit blaming us because we didn't do nothing. We've done this the whole time. Surge protection would be for something like where you have lightning strikes, or where you're switching capacitors on the line and you get a little ring, or where you're opening vacuum bottles, which open very quickly and they extinguish the current, and the magnetic field can't collapse immediately in the wires and all the systems out there, so it does like that. And it's not that big a problem these days. I mean, if you do a data center, you're probably going to have most of your stuff underground except for this up here. This may be coming in overhead. You'll want to put a lot of surge protection right here. You definitely want it there. And they make these really nice MOV gizmos that you can put in here that can accommodate 250,000 amps. But we've never had, to my knowledge at Oak Ridge, we've never had a problem with surge. It's always been voltage dips that have caused problems, because of faults on lines and stuff like that. And we've had lightning strike buildings. I stood there and watched it, hit lightning protection. Thing kept running. So with this UPS, I had to put a cold water storage because if I get a big power quality event, these chillers will drop offline. And when they drop offline, they got to restart. It takes them 10, 15 minutes to restart sometimes, maybe 10. In the meantime, you pump water out of your cold water storage tank while you're waiting on that, right? All right, it's really get expensive here. Put a generator up here. And if you lose power on this bus, this generator will pick up and carry that. So you got yourself pretty well covered for any eventuality, right? Loss of power, power quality events, whatever. In the TVA system now, if you're in Los Alamos, they're in the middle of the desert. They got a line coming from east and a line coming from west. If they lose power, they have tremendous amount of exposure up here to this. With us, we've got 5 161 lines coming in substation. Unless TVA's system goes down, we're probably not going to go down. So for high performance computing stuff, we said we don't need this and we don't need this. We just basically feed the computer cabinets right off the power line. But you're talking about 5, 6 megawatts to provide this stuff in the 5 or 6 megawatt capacity is prohibitively expensive. And it's a government research project. They don't ever have enough money to do what they're supposed to, and they sure don't have enough footprint. So we don't do this. This would be something you'd see at a banking institution, or financial institution, or Google or Amazon or somebody like that, where they've got paying customers that pay for that kind of reliability. And this is probably more like what you'd see with them. It's 2N plus 1. You got N UPSs plus a spare, N UPSs plus a spare, you got N generators plus a spare, and these generators can feed this way or that way. Your chillers have cold water storage, and they can be fed from either way. So you pretty much, if the equipment operates exactly like it's supposed to, you would probably never have a problem. But that ain't the way it happens. They had Amazon or Google, I don't know which one it was, had a big outage. And something happened to the power. And the generators came on, and they're parallel. They got all crank up, and when they get parallel, when the AC waveform gets in sync, they're all running at different speeds just a little bit. When they get in sync, they close them in. They got a synchronizer, like within 10 degrees. And come to find out, the synchronizing relay, which is a single point failure, wasn't working. They never would come online. So they sat there and just, you know, all that money they spent to get that kind of reliability, and one little doodaddy is all it took. And it's just so hard to make things indestructible. Smart money is to put another data center somewhere else in the country and mirror them and do like that and put your money in your communications between them. That's what I think. Now this is a different approach. Here's your power, IT stuff. Here's your chillers, switchboards. This is medium voltage switchgear that they call it source transfer, and it can find voltage on either side. If this side goes down here, this switch will close these switches and feed everybody from this way, right? You got generators up here if you lose everything. But the beauty of this is you're using a 13.8 kV UPS. You put 13.8 into it, 13,000 volts out of it. So you put it outside, and I'll show you one in a minute. Doesn't take up a lot of room. You can do 20 megawatts from one of these things. When you get these UPSs down here in the 600 volt, you get about 1,000 kVA per UPS, so you have to parallel them. And the most you can usually get is about 4 MVA, right? Then you got to parallel 4 of those to get 16. And you got to have a building for them, so it gets really expensive. This right here is very easy. And there used to be just one vendor, it's S&C. Now ABB is making medium voltage. Now I think they go up to 6 megawatts. Okay, let's talk about voltages. What is the voltage in that plug? Oh, sorry.
Sorry, I was just going to, so the UPSs will do power quality events, so surges or sags.
Yeah, yeah.
They'll handle both of those events.
Yeah, yeah. Double conversion UPS takes AC, converts it to DC, charges the battery, and then takes off the DC and reconstructs the AC. So whatever this does over here, it's kind of got a big sink where it dumps charge. And they've got ranges of voltages that they'll tolerate, you know. Then they'll go into the battery.
So generally that would be a good plan for us because that provides a lot of stability for a lot of different
Yeah, you really do need that. In part of it, you need that. Well, I won't jump ahead too far. I'm on 20. I gotta go.
None of those you showed were flywheel based.
No, I got one. I'll show you a picture.
You do have one.
I got a picture of one. It's very interesting, the flywheel. But what voltage is that right there? Blurt it out. Say it. I don't care. Huh?
110, 120.
110, 120. Okay, it's actually nominal 120 volts. People call it 110, 115. They call it 240, 230, 220. It's 240, 120. And there's standards that define that. Now in the computer world, you usually got, well, here's all of them. You got 120 volt single, 208 volt single, 240 volt, 277 volt single, 480 volt single. And then you got 240 volt and 480 volt delta, 208, 120 Y, 480 volt Y, 600 Y. You know, those are the kind of voltages you can have. But typically in a majority of data centers, we'll see 208 Y 120. Or they'll see 480 volt Y 277. Now that doesn't mean you got Y loads. It just means the transformer can take Y loads. You may just have a 3-phase load, in which case it would be a 3-phase 208 volt. A lot of the PDUs in your cabinets that you plug into the things under the floor will be 3-phase 208 without a neutral. So they go 208, 208, and 208, right? So all your equipment is rated for 208. And there's an interesting thing you can do on that. This is an interesting thing right here on DC voltage. It's 380 volts DC, and they fashioned the data center. And I encourage y'all to go to these websites and just click on them and look through this stuff. Large computers like the ones we have at Oak Ridge, we run them on 480 volts, 277 volt Y. And the reason for that is the power supplies are connected in a Y configuration with a neutral that carries current. The Y is 277 volts. That's just a little bit above 240 volts. If we put in a 480 volt power supply, they get much bigger because you got to have more spacing. And the breakers and the switches also have to be rated higher. Plus we're running 80 kW into a cabinet. You know, your cabinets are 10 kW. This is a good voltage for a 10 kW cabinet. But a 80 kW cabinet, it takes 8 of those wires go into a cabinet. So we run 100 amp circuit at 480 volts. So we use the 480 volt for the higher, bigger systems. And typically for a network, servers, disk drives, 208 volts, sometimes 230. And I found a website where they're basically taking 480 volt and converting it down to DC and putting batteries in the cabinet. So basically they got a backup in the cabinet, and they're busing 48 volts. And they're getting a lot of efficiency gains because they get rid of all the conversions up and down from AC to DC.
So what's the difference between 208 and 240?
240, okay.
Is there a difference?
Let me go forward here just a second.
Because I see those in
Page down. There we go. You see, this is a delta transformer I've got. These are the coils, and the wires are literally run from like that. If you trace the wires on a transformer, that's what they do. Now this is a 480 volt delta. On a 240 volt delta three-phase circuit, that's 240 volts across it, right? Now, at your house, that right there, well, that's 208 probably, because everything in the building is three-phase. But at your house, if you go out and look at the transformer, it's got 3 little lugs on it. And that transformer has, can I write on this?
You can. There's a pin there. Underneath. Oh, you have it.
Here we go.
Okay.
You got a transformer coil up here, and this is probably 12470 kV. That's KUB or whoever. Then you got a secondary on that transformer. And this is 120 volts here and 120 volts here. So when you go into your panel, you got a main breaker here and a main breaker here. This might be a 225 amp breaker. And you take, so between these two wires you got 120, but you got 240 here, you see. So that's how you get single phase 240. Now if you're doing a three phase, you'd have this would be 240, 240. You can have any voltage you want. They all usually are the same. And then what you do is you center tap one of these guys, and you do the 120, 120. And you really want to do something fancy, you can actually take this transformer out and still get three-phase 240 and 120. There's a town I had in Alabama where I managed utility, had a lot of industries, and they just needed a little bit of three-phase. Instead of running 3 lines to them, we ran 2 and put one of these up. But is that clear?
But you call it, you say 208.
Okay, 208 is three-phase.
208 is just
Three-phase. It's only going to apply to three-phase.
It's only
In the convention that's out there, when you go buy stuff, you buy 208. Now you can buy a 480 volt or 13.8 or whatever to a 208 volt transformer. You can do a single phase. You can do that. Like I say, you can buy any voltage you want. And if you bought, let's say you bought a 480 like this, and it was 208, and you could actually hook it up and make a transformer like this, where this is 480 and this is 208. You get 208 three-phase. But code requires you to ground one of these legs right here, because if you don't, there's all kinds of problems created. I'd love to talk to you about it, but it gets a lot of details, high resistance grounding and all that other stuff. So does that answer your question? Okay. So the 208 is for the three-phase. Typically in a building, typically in a building, you'll bring it in at 13.8. You go to a delta transformer, delta Y transformer, and this coil right here are on the same core. This coil and this coil are on the same core. And then that one steps down from 13.8 to 277. And the voltage you see across the coils is 277, but when you put them in this arrangement, because of the phase angles, and we'll do that in a minute, you get 480 volts across them. Okay? Now in Europe, they have 400 volts, 230 volts. And there's a direct relationship between, this is square root of 3 times this, always, okay? In Europe, that's the lowest, they don't have 120 volts, they got 230 volts. Most of your servers, disk drives, things like that are rated 230 volts. So they can use them in Europe, they can use them over here. And if you have a 208 volt system, or if you have 230 volt rack equipment, and you got 208 volt transformers, raise the taps on the transformers as high as you can get them. Because what you end up doing, here's the point your computer or whatever will drop out. Here's 208 volts. Here's 230 volts. You give yourself more headroom if you've got that and you're having problems with power quality events. Of course, we tried that with some and it didn't work too good, but in theory, it's supposed to work. Big dry type transformer. That's 2.5 MVA. Primary compartment goes to the transformer. It's got 3 great big old cores in here. And then this is a secondary breaker. It's 4,000 amp breaker. And you can see the cables coming out. This is the cable going in right here, a little cable about that big. And these are the cables coming out. So you can see what happens when you drop the voltage and raise the current. Same thing, except this is an oil field transformer. It's outside. This is primary switchgear. I got feeder here and feeder here, and I can pick and choose which one I feed the transformer with. And this is the secondary breaker, and here's the secondary circuits going into the building. Those conduits will go to something like this. This is a 480 volt switchboard. This switchboard is one of thousands switchboard. We got 4 of them. This is 4,000 amp. We got 3 4,000s and a 5,000 amp switchboard. Your power comes in here. Got a meter here. Here's your TVSS. Here's your transient voltage surge suppressor right here. We got one here. We got one on the switchgear. Another meter. We found that it's handy to have 2 meters because a lot of times you get your meters wrong and you don't know it. And you're billing people these massive amounts of money and you find out, oops, we should have billed them twice what we did. And I had that happen when I was in the utility business. How many of you know about heard about the Alabama band, right? Wow. Anyway, big band. They went all over the country. They built a big house. The guy put transformers in, and we set something called a CT meter. It wasn't directly metered. And I'm watching his power bill, and it's just nothing. And I sent my guys out there to check it, and they said, oh, meter's half what it was, what it should be. There's a multiplier that goes with it. So I said, okay, just change it in the books, and because the guy was a big supporter of community project stuff. And then I had a guy come through and check all my meters, and he said, you're way off. And I ended up having to back bill that guy about $10,000 in electricity, and he was not happy. So it's nice to have multiple meters to check yourself on, okay? These are 100 amp breakers and 20 amp breakers. They supply each cabinet, each computer cabinet, and that's 480 volts. And this is a switchboard. Switchboard, switchgear, you hear that term used. Switchgear is usually much heavier duty. You rack things in and out of it. A switchboard, you just direct mount stuff to it. We've used switchboards because, number one, the lower cost, and number two, we didn't have room because switchgear usually has to have access to the back of it. All right, this is a generator, 800 kW. It's a load bank. She kind of stretched it so it fit on here. This is a load bank. Soundproof enclosure, belly tank with about a day's worth of diesel fuel at full speed, full load. These generators here, because they're backup, are tier 1. Tier 1's just like they were 10 years ago. If you're going to use this to generate consistently and run all the time, you got to get a tier 4. And you know all the trouble Volkswagen's in right now. Well, that's the same thing it would have. You have to have, I think naphtha is what they call it, because it takes the nitrous oxide out of the diesel fuel. And the Volkswagen thing, they faked it because to get efficiency out of the diesel fuel, you got to raise the temperatures, and that increases nitrous oxide. So when they went to have the test done, they lowered the efficiency so they could lower. Let's see, yeah, what I'm trying to do. You know what I'm saying? They lowered the efficiency so they could get the nitrous oxide down, and it was done on and they had sensors in the car or whatever that could tell when they were testing it. It did do that, but when you got out on the road, it was giving you 51 miles a gallon. But the mileage dropped from like 51 to 40 miles a gallon. So a lot of people, because federal government's going to make them go with the more stringent controls. So people are going to lose 10 miles to a gallon. So nobody's going to be happy. Big mess, big mess. I always be honest. That's the best policy. They taught that. This is a transfer switch. You got a UPS and you got a generator and you got normal power. Normal power comes into the transfer switch and is normally feeding the UPS. If the normal power drops off, this transfer switch will say, hey, I've lost power. And it'll tell the generator to start, and as soon as it's running, it'll transfer the UPS over to the generator. And then when normal power comes back on, it'll transfer it back. And this is a 3-pole transfer switch. Boy, she cut off some stuff. I'm sorry, that was a 4-pole. This is a 3-pole. And this one has the capability of racking out the operator. So I can work on it, right? because you don't want to put stuff in you can't work on. For a computer center that can't be cut off, you got to have stuff to do. All right. This is a 500 kVA UPS. It's a Liebert NXL UPS electronics, and then you got batteries from here on back. Okay. And this is that manual bypass switch I was talking about. The static transfer switch is in here that bypasses the electronics of the UPS. Then you get it in static. Then you put it in manual bypass. Then you cut everything off. That's all dead over there. You can come in here and work on it, you see. That's why you have to have one of these. And that's about how much room it takes. And that room might look eerie familiar to you in some respects because and this is a 1000 kVA UPS. Sorry for the dark shade here. I took these pictures myself and didn't have the best light. It's a Liebert 1000 kVA UPS. This is flywheel backup, okay? And this is cute. This is the flywheel. They're like 200 kW a piece. They run for 16 seconds. And I got 8 of them, I think. And the beautiful thing about it is when they're running, they only draw 7/10 of a kW, 700 watts. They're very efficient. You don't have to replace them. You don't have to change the batteries every 5 years. They just sit there and run. Now, what you don't want to do is put them on a computer floor and have some guy drop a 3,200-pound computer cabinet right in front of one of them because they're riding on magnetic bearings and they go, and it messes up the bearings. We had that happen, by the way. But the interesting thing about this, it's a carbon composite drum, and it's spinning at 52,000 RPMs in a vacuum. That is fast, right? Okay, you know how they measure the vacuum? They spin the drum up to a certain speed, and then they cut the motor off, and they let it coast. And then they measure how long it takes it to coast down to a certain speed, and then they spin it up again. And if it coasts too fast, then they can actually tell you what the vacuum is and how many torque or whatever. And once you get them evacuated, you know, they just pretty much sit there and run forever. But flywheels are good. Now, a generator, a big generator, we got a 2200 kW, 2 megawatt generator, will actually crank and come online in 7 seconds. I mean, it's a monster. I mean, it blows smoke out and it shakes the ground, but it's spinning and delivering 480 volts to the UPS in 7 seconds. So you don't need a lot of time. Now, where you'll see I've actually been in places where they had buildings that were full of batteries for their UPSs, and they had to run like 30 minutes because they had a bunch of generators that got off battleships, and synchronizing those things was a dog. You know, they had about 10 generators in parallel, and they'd have to wait 30 minutes before they get them all synchronized, so they had to have UPS that run long enough. This one right here has got 1 generator on it, 7 seconds. I just need 16 seconds of UPS because if I don't get the generator started in 16 seconds, it's probably not going to start, and it don't matter anyway. This is a medium voltage UPS, S&C. This is the medium voltage switchgear. Your incoming lines down here, your outgoing lines here, and then it feeds to these 4 modules. These are 2 megawatt each. So this is an 8 megawatt UPS. And it's basically taking the utility service, running it through the UPS, and then sending it into the building for computers, chillers, or whatever else. In other words, they're pretty much, and this one will last about a minute, okay? You gotta replace the batteries every 5 years. You can tie it into a generator on the front end. You can have multiple feeds. You can do all kinds of stuff. It's pretty neat because, number one, you don't have to build a building for it. You don't have to air condition it. You just sit it outside on a pad. You interface it into 13.8. It's really not a bad concept. Now, this one's a standby UPS. It's in static bypass all the time. And it's watching the power line. And every 20 times a cycle, it samples the AC waveform. And if it sees a 10% RMS voltage drop, it basically cuts the UPS on, and the UPS starts feeding the load, and the static transfer switch cuts off in about a quarter of a cycle. Now, most of your computer stuff, a quarter cycle, you can cut the power completely off and cut it back on for a quarter cycle, and it'll ride through it. Just about all your stuff will, because it just can't deplete the energy in the capacitor banks that fast. So this thing right here works good. It's very efficient. By going through the static bypass and not through all the electronics, instead of having a 96% efficiency, you got a 99% efficiency. So if you're talking about 10 megawatts, that adds up to a lot of money. Okay, these are PDUs. Transformer with breakers that feed RDUs. This is a PDU with a transformer in the back, and it's got 4 panel boards. These are 208 120 volt panel boards, okay? That's what you'd put on the floor. And there's an RDU. The one on the right would feed these panel boards. All it's got is panel boards. Now, quickly talk about calculations. I'm about out of time, aren't I?
You got 4 minutes.
4 minutes.
3
Okay.
minutes.
Okay. This is real simple. Don't try to understand it, just believe it. I'm going to go to That was a lesson I learned in school. Quit trying to understand it. Believe it, memorize it, and later on you'll figure it out. All right? That's my advice to you. Here you go. This is power. And when you run current down a wire, there's always a magnetic field. Always a magnetic field. Now, if it's DC, it's a steady magnetic field. But if it's AC,